We're going to begin today by reviewing a couple of vocabulary words that we learned back earlier in the year. They're on the board here: empirical formula and molecular formula. Now you might remember that the empirical formula is the lowest whole number ratio of atoms in the compound. And we had to use that kind of formula whenever we were doing anything with ionic compounds, because ionic compounds don't form individual molecules. Ionic compounds form great big clumps of billions and billions of ions all clumped together, and there aren't individual molecules there. So the only way to represent that kind of compound is to use subscripts that just give a ratio. So for example, in sodium chloride, there's always the same number of sodiums as there are chlorides, so we just represent it with a 1-to-1 ratio. But in calcium chloride, there's 2 chlorides for every calcium, so we have to represent it as CaCl2. So that doesn't mean we have individual molecules that have 1 calcium and 2 chlorides in it, but it just means that in our big clump of ions, there's always twice as many chlorides as there are calciums. And you might remember that that had to be true because the calciums have twice as much charge, so we needed twice as many chlorides to even off the charge. Molecular formulas, on the other hand, are not used for ionic compounds, but those are used for molecular compounds. And we get into a situation where we do have substances that have those covalent bonds in them, and they have a particular number of atoms in the compound. So every molecule has a particular number of atoms, and there might be many, many of those molecules next to each other, but there are individual molecules that have a certain number of atoms. And so we don't necessarily use an empirical formula. Empirical formulas are not the best way to represent those. Now, it is possible to take a sample of some unknown substance and analyze it in a laboratory and come out with how many grams of the different elements were in that sample. So if one were to do that and get that kind of data, then one would want to be able to take that data and say, okay, well then I can figure out the formula for this compound. So that's what we're going to do today. And we're going to start with this example over here. So this is a compound that's been analyzed. We don't know what it is yet, but we know it only had nitrogen and oxygen in it. And when it was analyzed, that sample was found to have 4.9 grams of nitrogen and 11.2 grams of oxygen. Now, what are we going for here? We know that our formula will have a nitrogen and an oxygen in it, and we are trying to figure out the subscripts. Now, the subscripts represent a ratio of individual atoms, in other words, a ratio of particles. We can't get there from grams. We could get there from grams if all atoms had the same mass, but they don't. They're all different sizes. And so therefore, in order to get a ratio of particles, we have to use moles, because moles are like a count of the number of particles. But lucky for us, we know how to do that. We just learned that. So let's take what we just learned and convert these gram numbers into moles. So we've got 4.9 grams of nitrogen, and we divide that by the molar mass. Now you remember that the molar mass is the same number as the atomic mass. It's just in grams instead of AMUs. And we find that number on the periodic table. So if you look at your periodic table, you will see nitrogen has a molar mass of 14.0 grams in every mole. So we'll divide this by 14.0 grams per mole. So in 1 mole, there's 14 grams. Now we only have 4.9 grams, so clearly we don't have a whole mole of this stuff, but we'll find out what we've got in a minute. And then we've got 11.2 grams of oxygen. And again, looking at your periodic table, you'll see that the molar mass for oxygen is 16.0 grams per mole. So now we pull out the calculators and do a little math. 4.9 over 14 is 0.35. So that's moles of nitrogen. And 11.2 divided by 16 is 0.7. So they've given us easy numbers here, and it's pretty easy to just look at this and say, well, that's a 2-to-1 ratio. 0.7 is twice as much as 0.35. But sometimes we'll get numbers that are not quite this easy, so I'm going to go ahead and go through the process that you would use if you got numbers where you couldn't just eyeball and say, oh, I see the ratio there. What you're going to do here is take whichever one is smaller and divide both of the numbers by that. So I'm going to divide this by 0.35 to get 1, and I'll divide this by 0.35 to get 2. And that's really what you're kind of doing in your head when you see right off the bat that this is twice as big as that. That's what you're doing in your head, even if you don't realize that you're doing that. So we have got a 1-to-2 ratio here, so that means that nitrogen would have a subscript of 1, which at this point we know is not shown, and oxygen will have a subscript of 2, which is shown. So we have just found out the empirical formula for this substance. That doesn't necessarily tell us the molecular formula, though. So to get the molecular formula, we need one more piece of information. And that, again, is something that you can get in the laboratory even if you don't know what the compound is. There's an experiment that you can do that we'll learn about later this year, maybe. Pretty easy experiment where you can just find out if I dissolve so many grams of this substance in water and then boil the water and measure the boiling point, there's an equation that you can use to say the boiling point has changed by this much, and I can use this equation to calculate what is the molar mass of the substance. Without even knowing what the substance is, you can get the molar mass by doing the experiment like that. It's kind of cool. So anyway, but we're going to be told in the problem that the molar mass for this material is 92. So what we have to do is compare that to this. Would the molar mass of this be 92? So nitrogen's 14, oxygen's 16, and there's 2 of them, so that's 32. No, the molar mass of this is only 46. Well, how do these two compare? It looks like this is twice as big as that, doesn't it? So if this is twice as big as this, that means this molecule needs to be twice as big as it is in order to have the molar mass that we're told it has. Well, that's an easy fix. We need to keep the same ratio, and it still needs to be a 1-to-2 ratio, but we need to make it twice as big as it is. So to do that, we can just say N2O4. So we still have a 1-to-2 ratio, but now we have enough atoms so that if we add those all up together, we'll get a molar mass of 92.